Let's talk about specific heat. This is for the Chemistry PACE 1123, which is the third PACE in the chemistry course. And we're on pages 4 through the top of page 7. So what is specific heat? By definition, it is the amount of heat you have to add to a substance to raise the temperature of 1 gram by 1 degree Celsius. Okay? Now, in the previous video, we talked about this, and this was kind of like, similar to the definition for a calorie. A calorie was only for water, so I want to make that clarification. Whereas specific heat can be applied to not only water, but lots of other substances, okay? Often it's with metals and determining how fast, how much heat it takes to raise the temperature 1 gram, all right? Every substance has a unique specific heat value that you can look up. In fact, there is a chart, and while I'm talking, I'm trying to find it here. It's on the top of page 5, specific heat of selected substances. Find water on there, water liquid. Notice that that's 4.184 joules. That's kind of a high number compared to the other things on the chart. Look at that. Most of the things on the chart are less than 3, 2.45, 2.048, and then the whole right-hand column is less than 1. So gold, which is not even on the chart, actually is even lower than anything on the chart, 0.13 joules. What that means is it doesn't take much heat at all, very little energy, and boom, it absorbs the heat and the temperature goes up, okay? Water actually takes a lot longer to heat up. So if you put a hot pot, a frying pan on the stove, and you start adding heat to that, and next to it you have a pot of water, and you're adding the same amount of heat to that at the same time, if you put your finger, don't try this, but you put your finger on the frying pan, it's going to feel pretty hot. You're going to burn your finger. Whereas you could put your finger in the water, and it's going to take a while. It's going to start getting warm, and a little bit warmer, and it's going to take quite a while until it actually boils. Now, notice in the middle of page 5, there is a formula, and we're going to come back to that. It says Q equals Cm delta T, okay? And so the C is the specific heat. It is a number. And so if we're talking about iron, then we need to look up this C for constant from table 3.3. So for iron, it would be 0.444 that we would use in that formula. Now the PACE has this picture, and I just want to point out, it's kind of a fun explanation here. If we took different blocks of metals, like obviously this is aluminum, Fe is iron, we have copper, zinc, Pb is lead. And if we add the same amount of heat to these blocks, let's say we put them in a frying pan and we heat them all up to the same temperature, and these are all basically the same mass. Now they look like a different size. That's because aluminum is a lot less dense than some of the other metals. So they all have exactly the same mass. We've added the same amount of heat to all of them, and then we lay it on some wax. That's what paraffin is, paraffin wax, kind of like candle wax. And when you lay it on there, it is going to start giving off heat and melt the wax underneath it and start sinking further and further, deeper and deeper into the wax, okay? So the aluminum actually looks like it absorbed more heat, and so it's going to give off more heat and sink further down. Mr. Anger, what are those units? J/G dot degrees Celsius. Yeah, it's called joules per gram times degrees Celsius. Really, all we have to focus on is to make sure that in the rest of the problem, all the units are consistent with that. The energy, the Q, is going to be given in joules. The mass has to be in grams, not kilograms. Temperature has to be in degrees Celsius. When we do that, we don't have to worry about the units so much. We really can just plug in that number, and all the rest of the units will cancel out because of these particular units. And then we'll get the answer in the units that particular quantity. Like if we're measuring for Q, it's just going to come out in joules. That's all we have to know, okay? So don't get too concerned about these units. Just make sure that your problem starts off with these correct units. All right, here we are, middle of page 5, and this is a very important formula. Highlight it, put a box around it. We're going to use this a lot. Notice we have 4 things. The thing on the left is Q, that's the heat. We measure that in joules. C is that constant, it's from the table. We will always look that up, okay? If we solve for it, it's for the purpose of then taking the number we find, comparing it to the chart to see what substance it is. M is always mass. We measure that in grams, and then the delta T goes together. Remember that? The triangle T is one thing, is the change in temperature. The fact that they're all smashed up one against the other means that we're going to multiply them together. So they show us here then, given, what if we had 500 grams of, looks like water in a beaker, and it's 80 degrees Celsius. We know that the water's C value is 4.184. And compare that to a basin. I think this is going back to the picture on the top of page 4. And if we had a basin of water that was, look at the mass there, 100,000 grams, that's a lot more. They didn't put grams there, but they should have. Unless they were only raising the temperature 4 degrees, still water, so 4.184. And then if you multiplied that together, notice the answer you get, 1,670,000 joules, whereas the beaker of water, it's about the size of a coffee mug, would be 167,000 joules, even at the higher temperature. So even at the higher temperature, we have less thermal energy, joules, than a basin with a lot more water in it at a lower temperature, 4 degrees Celsius, okay? Just an interesting factoid there, but they're showing how they use that formula to compare the amount of thermal energy. Now we're going to talk about a very important concept, and that is, where is it? Calorimeters. And calorimeters are based on this concept of the conservation of energy. Energy lost by one object, like a cup of coffee cooling off on your desk, that thermal energy goes somewhere, it goes into the air. So actually the air technically heats up with the same amount of thermal energy being given off by the coffee cup. So if we can insulate the surroundings, then the only change is coming from the object. So if the object cools off, we could measure, for instance, the water that it's in, and that's absorbing the heat. This is a picture of a calorimeter that I use here in our school's science lab. So there's an outer cup, and then this is like a cup that fits inside of here, and there's this black ring that kind of holds it away so that there is air trapped inside there, and that's the insulation. And then this wooden lid fits on top. There's 2 holes. This one is for a thermometer. And then we have a stir stick that can go through the other hole. So in a calorimeter, the water would be at room temperature. We would just let it sit. At room temperature, it's not going to get any colder. It's not going to get any hotter. There's no change that can take place. Okay? Then we take a hot object that's been sitting in maybe on the stove in boiling water, and it's reached 100 degrees Celsius. If I take that chunk of metal off the stove, it's 100 degrees, and I put it into the calorimeter in the water, the heat is going to transfer from that hot object, and it's going to gradually heat up the water. Now, it's not going to be a dramatic change in the water, but it's going to heat it up a few degrees. At some point, the metal will have cooled off, given off some thermal energy. The water absorbed that thermal energy, which raised the temperature a little bit, and then it reaches what is called equilibrium. okay? Equilibrium. And we can measure the final temperature. The final temperature of both the object that we put in, that was hot, now it's neutral, and the temperature of the water are the same temperature now, okay? That's the final temperature. And then we can calculate how much heat was transferred using the formula on the next slide. So if you'll notice here on page 7 at the top, M with the subscript M means the mass of the metal, okay? MW is the mass of the water. And if you read the problem here, they're saying that the metal has cooled off negative 101 degrees, and the water has warmed up in the process by 4 degrees. Now we already know the C value for the water. We looked that up on the chart, 4.184. We're going to figure out what is the C value for the metal. That's the unknown. So here's the formula down here. Notice they're multiplying. Now, remember what Cm delta T is? That's the Q value. Okay, so the heat, literally the heat of the water, has to be equal to the heat of the metal. Look at, we have a negative out front here. You see that? It talks about that over here. That just means that the metal is giving off heat. So that's why it's a negative value. See the dot, dot, dot? That means therefore. Now I want you to notice what happens in this step right here. We have the water's thermal energy, Cm delta T, and we're dividing by only the mass and the change in temperature of the metal. That's what's on the bottom in the denominator. So if you look right here, you see all of the numbers that they're plugging in, and that came from up here, okay? Use your calculator, multiply these 3 numbers together, multiply the bottom 2 numbers together, and then divide the top by the bottom, and we get negative 0.899. Now that is the negative C value, which is the specific heat of the metal. So if we just drop that negative sign, we have 0.899. So now all we have to do is go back and look at that chart on page 5. We look up 0.899. Aluminum! We just figured out that this metal was aluminum, okay? So a little bit of math there. Hopefully, if you follow each of the steps and be very careful to follow what each of those variables stand for and how they found the numbers from the chart above and just plugged in and solved. And you're going to do a few problems like this in your homework. All right, so hopefully that will make sense and you can do well on the problems coming up.